Hello, so we are back with the second part of chapter 17 discussions. And here we are actually now trying to see what happens if you have like sound waves, not like any general mechanical wave, but just sound waves, okay? Creating the standing waves or superposition using the superposition principle. Now, you can have sound waves superposing in three different scenarios. In places where you have like, think about a closed chamber, okay? So um, this could just be a pipe. This could just be a pipe which is closed at both ends and you are looking at the cross section of it, okay? Now, if you have such a scenario, right, your um, length of the pipe will of course show up in the fundamental frequency or the mth order frequency, let's say. And but we have to understand how this pressure difference is creating the nodes and antinodes in these different structures, okay? So for example, in closed format, you have antinodes in the two ends, pressure antinodes in the two ends, and the pressure node in the central part. When you have pressure node, you have actually the displacement antinode in the middle, and you have displacement nodes in the in the two ends, right? So this is m equals to 1. Now, if I have to understand from where we are getting all these expressions, it's easy to find out that, right? So if you have a node here, if you have and you have another node here, we know that two nodes are separated by a distance of lambda over 2. That was the definition of nodes, right? So when you have m equals to 1, right, you can call this lambda 1. Lambda 1 is just basically lambda 1 over 2 is basically L, right? So this is lambda 1. Lambda 1 over 2 is the distance between these two guys in the space coordinate, which is basically this length, right? And that length is the length of the tube. So you can say lambda 1 equals to 2L over 1, right? Similarly, if you go to a higher order, m equals to 2, your expression will be lambda 2 equals to 2L over 2, and so on and so forth. If you go to 3, 4, 5, any of them, your general formula will basically become 2L over m. Whatever order you're looking at is showing up in the denominator. So that's why it is 2L over m. And once you know the lambda, using v equals to f lambda formula, right, you can always find out f, which is mv over 2L. So this is how you work with closed pipe. And once you understand one of the cases, it's very easy to understand the other cases. So it's open and open, both ends are open. Think about a flute, right? So in that case, you have basically displacement antinodes here, right? So you have one node, you have one antinode here, you have another antinode here. Basically, two antinodes will also have lambda over 2. So that's why it will be very similar to what you have already seen in the previous slide. But generally speaking, this is lambda over 2. This length is, for the first order, you have lambda 1 over 2. And then you can equate it with this guy to get to generate the first formula. So lambda 1 is again 2L. And similarly, you can actually find out all the different orders just by changing the number of nodes in each of these cases, right? So if you go to this one, for example, you have antinodes you have node, you have another node, and you have an antinode. So two nodes are separated by lambda over 2, right? And this is m equals to 2, so I'm calling it lambda 2. Lambda 2 over 2. Then you have this length to be equals to lambda 2 over 4. And then you have this length to be equals to lambda 2 over 4. So if you add all these things, these two are going to give you lambda 2 over 2, and then lambda 2 over 2 is that whole thing is basically lambda 2. So lambda 2 equals to L in this case. And you can actually call this equals to 2L divided by 2, so that you can generate a formula of 2L divided by M, and then you can suddenly like construct all the different order formulas very easily from here. So this is how you generate all these expressions. I want you guys to go through these discussions from the textbook so that you understand the derivation. And the final one would be closed open, or one end closed and one end open. And very similar logic will give you like the three expressions, that the fundamental frequency and all the higher order frequencies, and then the lowest wavelength and all the different wavelengths as well, or the highest wavelength and all the different wavelengths as well. And similarly, you just use always the same parameters. You first look at the, always look at the blue curve here, which is basically the displacement graph. And this displacement graph will give you the positions of the nodes and antinodes. And using the fact that two antinodes are separated by lambda over 2, and one antinode and one nodes are separated by lambda over 4, you can actually find out all the different ratios. And that's how you actually get all these different musical tones from either piped instruments or stringed instruments. It doesn't matter what kind of instrument, musical instrument you're using, you're generating always some sort of a standing wave inside it. You're always using the standing wave to generate these sounds. And for the string, a very important formula to remember or to put it in your equation sheet is the fundamental frequency, which is 1 over 2L square root of Ts over mu. And Ts here is the tension, okay? You might have seen people who are musicians who play like stringed instruments, they tighten these bolts, right? So that they can adjust the tension. And if they adjust the tension, that changes the frequency. If they are calibrating the instrument before the performance, or even during the performance, if something sounds not completely in tune, then they adjust these guys, they adjust these bolts so that they have a correct tension and the correct frequency. And mu is the linear mass density, which is m over L. Okay. All right, so with the wind instrument, yeah, I don't think these are like anything new. This is basically what I have been talking about, how you can different harmonics from the fundamental frequencies. And that will bring us to the next, probably the last part of this, last section of this discussion, where we are talking about interference of sound waves. What happens if you now have two sound waves moving in the same direction, right? They're not moving in from two different directions. They're not moving like head to head. They're now moving in the same direction. And if they do that, there is a possibility that they can cancel each other at some places, and then they can also reinforce each other, right? So in order to understand this, in order to understand interference, this is nothing but simply superposition principle, superposition of two sound waves. But in order to understand this, we're just going to quickly take a look at mathematical expressions, which is basically you have two waves, D1 and D2, right? They're both moving in the same direction. Of course, they have slightly different phases. So you can see that the first wave has already traveled to here where the second wave is coming up, right? So they have a phase difference between them. So that is what we are signifying by phi 10 and phi 20, okay? But generally speaking, the superposition principle is still valid. So if you want to know the net displacement of the medium at a certain point where these two waves are overlapping, you would just add these two guys, right? The two waves are in phase, meaning that d1 equals to d2. They're in phase, right? They're moving in such a direction that they overlap. So look at this wave, okay? It matches exactly where this wave would have been a little bit ago, right? So what I'm trying to say here, or what you are going to see here, if they're overlapping, that they're going to constructively add in all places. They're going to interfere constructively at all places. And that's why you can see the blue curve, which is basically summation of these two waves at every point, right? So they're not canceling, so to speak. This is not a standing wave. They are still reinforcing each other because of the slight phase difference. They're not like the same wave moving in tandem. They are just one after another, but they're shifted in such a way that they match each other. They're shifted in period in such a way that they still match up over here. The resulting amplitude is 2a for maximum constructive interference, right? So if this was the small amplitude for one of them, this was the small amplitude for the second one. If you add these two, you're going to get a large amplitude. And in case if they are out of phase, this was in phase. If this was out of phase, for example, if this second loudspeaker was positioned in such a way that at every place, these two guys are going to cancel each other, just like from what we have already studied, we're going to get a zero intensity or zero displacement, right? So you have a perfect destructive interference. And that's how you get it. So d1 plus d2, you plug in the sinusoidal functions, the sine waves basically, and then you look at the amplitude part and look at the wave part, right? This is just the pure amplitude part, and the amplitude part depends on the phi, which is the phase difference. Delta phi is the phase difference, right? And depending on how much, if they are in phase or if they are 180 degree out of phase, this guy is going to give you either 1 or 0. Basically telling if this is 2a or if this whole thing is 0. So generally speaking, your conditions, the condition that you will have a constructive interference or a destructive interference will always boil down to this, will always boil down to if your phase difference is like an mth multiple of 2 pi, an integral multiple of 2 pi, or if that is if that is m plus half times 2 pi. So if this is like half shifted from the mth integer, or if this is just mth integer, will give you either maximum or minimum amplitude. In the problems, you're going to see a lot of cases where you will have to decide if they're talking about maximum or constructive interference or perfect destructive interference. And depending on what you decide, you're going to use that formula. So it's very important to understand when you are looking at constructive interference, when you are looking at amplitudes being doubled or amplitudes being 0. Okay, so applications for that comes from all the different aspects. One of the way we basically understand interference is by looking at optical interference. And I think I'm going to actually discuss about, I think I'm going to just discuss about this one, this part of the thin film optical coatings in this segment, and then we'll move forward with any subsequent 2D and 3-dimensional superposition principle discussions, okay? So technically speaking, thin transparent films For example, if you have like a thin soap bubble or thin film of anti-reflection coating, just something that you see in your spectacles on glass, right? So what is going to happen if you have a wave, a light wave that is coming from air to the interface of air and the thin film? What is going to happen if it is moving from left to right? So when it is moving from left to right, part of the wave reflects back with a phase shift of pi radian. Part continues into the film, and it depends how much phase shift you will have. It depends on the density, okay? Anyway, we are going to look at the refractive index and the density later on. But what happens is the part which continues, of course, you can see that the part that is continuing has a slightly different lambda, right? So it will go on and then it will again have another reflection from this interface. So you have now one reflection, two reflections, and these two reflections are overlapping. When these two reflections are overlapping and they come to your eye, you're going to see some patterns, some light patterns, some optical patterns, which are as like basically which are a result of these two different surfaces being present in the system. So anti-reflection coatings on the lenses in cameras, microscopes, and other optical equipment are examples. And in order to understand, in order to decide what kind of which kind of constructive or destructive interference we are looking at, we will have to first find out the phase difference between the two reflected waves, okay? And the phase difference is 2 pi 2nd over lambda, where n is the refractive index of refraction of the coating, d is the thickness, and lambda is the wavelength of the light in vacuum or air. So imagine if you are given a problem with 800 nanometer or 400 nanometer or 500 nanometer. So you are going to use that wavelength value in these problems. Imagine if you are given a glass refractive index, then you will use 1.5 in n to solve that problem. For a particular thin film, constructive or destructive interference depends on the wavelength of the light, of course, right? So for constructive interference, you have 2nd over m. For destructive interference, you have 2nd over n minus half. And m is again the order of interference. It could be 1, 2, 3, and many others. A lot of these concepts are going to be very evident and clear when we are solving problems. So I would actually wait and understand this with the help of like exercise problems that we're going to solve, because there's a lot of different conceptual things that we will have to understand when we solve this. So that brings us to the very last segment. I'm going to actually stop here and then come back and cover the rest of the like 10, 11 slides that we are left with. And so stay tuned, and I'll see you in the next segment, the last segment of chapter 17.